Let's continue with ZEUS training, section 16, examples for complex configurations. Okay, our first test case here will be subsonic, transonic, and supersonic aerodynamics of the L56A18 wing body tail configuration. So this is the aircraft here. The purpose here will validate the lift, moment, and drag of the L56A18 wing body tail model with wind tunnel data, and we'll demonstrate how to generate one block of mesh for modeling the wing body tail configuration. The coplanar wing body tail model is adopted from the NACA RM L56A18 report. The wing is mounted in the mid-wing position on the fuselage and has no geometric incidence, dihedral, or twist, and the body is modeled by one Body 7 bulk data card. The fuselage consists of a cylindrical body of revolution, having an ogival nose and a slightly boat-tailed aft body. And the horizontal tail has an aspect ratio of 4, a taper ratio of 0.6, and a NACA 65A006 airfoil section parallel to the plane of symmetry. And the horizontal tail is mounted in the mid-fuselage position at an angle of incidence of -4 degrees. So this is the surface panel model of the wing and tail. The wing is modeled by a CAERO7 bulk data card with ID 5001. So that card is shown here. This divides the wing into 42 chordwise divisions and 29 spanwise divisions, which gives us 41 times 28 boxes. And it refers to the PA Foil 7 card with ID 4111, which is shown down here. And this PA Foil 7 card defines the NACA 65A004 airfoil section. Next in the CAERO7, we have the X, Y, and Z coordinates of the root leading edge, the X, Y, and Z coordinates of the tip leading edge, and then the root chord and tip chord. Next, the chordwise cuts at the root are defined here to align the body, with the body axial stations. So this will give us a consistent Y lines in the mesh. And then the spanwise cuts are specified by the AE Fact 501, which is shown here. And this is to align with the cuts of the tail, so that we can fit the tail and the wing in the same blocks. Now the horizontal tail is divided into 15 chordwise and 17 spanwise divisions, which gives us 14 times 16 boxes. And the CAERO7 bulk data card has an ID of 7501. And the NACA 65A006 airfoil section is specified by the PA Foil 7 card with ID 6111. And it's referenced right here. And then the 17 spanwise cuts are specified by the AE Fact card with with ID 751. So that reference is here. And the spanwise cuts here are specified to align with those of the spanwise cuts of the tail. Now the alignment of the spanwise cuts between the wing and the tail is necessary to avoid extra spanwise X-lines being generated in the final mesh, because the extra spanwise X-lines may decrease the mesh quality and lead to convergence problems of the flow solution. Next we'll look at the body. The body is modeled by a Body 7 bulk data card with ID 1001 shown here, that refers to a segmesh card with ID 1. And this divides the body into 84 axial stations here and 9 circumferential points, which gives us 83 times 8 boxes. Now within these 84 axial stations, there are 42 axial stations at the wing and body juncture, aligned with the 42 chordwise divisions of the wing root, shown here. So we line up the cuts to avoid extra chordwise Y lines being generated. Now the segmesh bulk data card defines the YR shrink to be 36, YL shrink to be 0, ZT shrink is 36, and ZB shrink is 36, and then reduce is 0.5. And shrink equals all for all of the X stations ahead of the wing, and this is to define a region within which the spanwise and horizontal X lines are sheared to accommodate the variations of the body width and height. So the shearing will only take place ahead of the wing, and then starting at the wing leading edge and aft, the lines from the fuselage are not sheared. So we'll see that a little bit later in the final mesh. Next, we'll look at the surface panel model and the computational surface mesh. So as we just saw in the previous slide, you can see how this region, the body box is sheared to follow the body, and then from the wing and aft, it just stays straight. So the plot arrow card with ID 7001 and mesh equals no is specified to generate the tech plot file shown here. And this is the aerodynamic surface panel model. And then the computational surface mesh along with the slope contour ds dx can be generated using the plot slope card, and that is shown on the right. The surface panel model is used to generate the computational surface mesh. Now in the computational surface mesh, the CARO7 macro element is modeled as a flat plate, and the body 7 macro element is modeled as a rectangular box, as seen. And the volume mesh is automatically generated from the computational surface mesh. In the volume mesh, the transpiration boundary condition is applied on the computational surface mesh. And after the Euler solver solves the Euler equation, the aerodynamic solution on the computational surface mesh is interpolated back on the surface panel model. Therefore, the aerodynamic solution is always presented on the surface panel model. That is, the aerodynamic force and moment coefficients are computed by integrating the pressure distribution on the surface panel model. So next we'll look at the volume mesh generation. Now because there is no overlapping region among the wing, body, and horizontal tail on the projected XY plane and the YZ plane, the L56A18 configuration can be modeled by just one block of mesh. So we have a single block card shown here with ID 1 that generates this block of mesh with the computational domain from X equals minus 100 to positive 500, Y from 0 to 150, and then Z from minus 150 to positive 150. And then we have 3 Y zones specified. The first Y zone covers the spanwise range from Y equals 0 to 4.765 in which the body is located. So the 4.765 is the root of the wing right here. And so the first Y zone is here. And the only component in that Y zone is 1001, which is the body 7. For the boundaries, for the first, the left side of the Y zone 1, we're just using a real number, 0.0. And then for the remaining Y boundaries, we're referring to the Y zone Y cards. So we're using the wing, the left hand side of the wing determines the Y zone Y ID 1. So we use that as the right hand boundary of zone 1 and the left hand boundary of zone 2. And then the 2, we're using the right hand side of the tail. So 7501 is the ID of the tail CARO7. So the right hand side of the tail defines that boundary. So that's this line. So we're using that as the right hand boundary to Y zone 2, and Y zone 2 includes the wing and the tail. And then that's also the left hand boundary of Y zone 3. And then the right hand boundary of Y zone 3 is defined by the Y zone Y card with ID 3, which is the right side of the wing with 5001. And then graphically we can see that here. Now the density of the mesh is controlled by the mesh param card with ID 10 that refers to the block card with ID 1. This defines the mesh size near the surface mesh and the growth rate of the mesh from the surface to the outer boundary of the block of mesh. And then using these mesh density parameters, the total number of grid points generated by the automated mesh generation scheme is 116 by 51 by 45. So in ZEUS, you do not specify this 116, 51, and 45. You only specify the mesh growth parameters in the mesh param card and the boundaries of the block. And then using these boundaries and the mesh growth parameters, ZEUS will grow the mesh, and then after the mesh is generated, then you can see how big the resulting mesh actually is. So here we'll look at the volume mesh. So we have a plot arrow card with entry mesh equals yes to turn on the volume mesh plotting. The chordwise Y lines ahead of the wing leading edge and behind the wing trailing edge and the tail leading edge are originated from the axial stations of the body in these regions. And this is the reason why the refined axial stations of the body ahead of the wing leading edge and behind the trailing edge are used. So that gives us some more cuts ahead and behind the wing. And then the refined axial stations, when they are extended into the volume, can provide the compatible mesh sizes of the chordwise Y lines across the wing leading and trailing edges to enhance the solution accuracy in those regions. And then the spanwise X lines are sheared to accommodate the variation of the body width and height ahead of the wing leading edge. So we saw that in the seg mesh card. The shrink option was set to all for these axial stations, so you can see how the mesh is sheared to follow the fuselage. And then you can't see it in the vertical direction, but it's also sheared in the vertical direction as well. And then you can see behind, starting at the wing leading edge and aft, the X lines are not sheared. And then this graphically shows our body box. So next we need to talk about the pressure extrapolation on the tail, because you may have noticed that the fuselage gets smaller behind the wing and the tail extends inside this region. So the width of the box to model the body in the computational surface mesh is wider than that of the body in the surface panel model at the body-tail junction. So this means a part of the tail near the root is inside the box, and that's this portion right here. Now because our body box, shown by the blue line, is out here, no flow solution is computed inside this body box. So this implies that no solution is available along the strip at the tail root located inside the body box. So this strip right here. However, the program will interpolate and extrapolate the solution from the computational mesh onto the surface panels. So this part of the horizontal tail surface panels inside the body box will still have a flow solution due to the extrapolation of the flow solution from those nearby panels on the tail. So this is the reason why the width of the first strip along the root of the tail surface panel model is large, so that only this strip is inside the body box and the rest of the strips are outside the body box. Now this pressure extrapolation could be avoided if the tail is modeled by an embedded block in the main block that only consists of the wing and the body, and then the fuselage body uses the shrink option behind the wing. So if we enabled the shrink option behind the wing, then the body box would be shrinking back here, and then the boundary would be back here, so that these panels would no longer be embedded inside the body box. However, if we do that, we then cannot embed the tail in the main block anymore because ZEUS can't handle this shearing action to embed the two components within each other. So that means the tail would have to be in a separate block, and that would require a 2-block overset mesh. And the overset mesh may decrease the flow solution accuracy and should be avoided if possible. So in this particular instance, it's better to put the tail in the main block and then extrapolate the flow solution onto these panels than to activate the shrink option so that we can compute a flow solution on these panels, but then have the tail in a separate block. So next we'll look at the control surface input. Now to introduce the -4 degrees of incidence angle of the horizontal tail into the analysis requires the definition of the horizontal tail as a control surface. And this is achieved by specifying an AE_Z bulk data card with the entry label equals HTail. Now this refers to the PAN LST3 card to list all of the surface boxes of the horizontal tail as the control surface. And the hinge line of the control surface is defined by the z-axis of a Core 2R card. And the plot surf card is used to generate a tech plot file that stores the surface panel model with the deflected horizontal tail, and that's illustrated here. And the control surface is referred to by the trim FLT card to include the effect of the -4 degrees of incidence angle of the horizontal tail in the transpiration boundary condition. So now we have the input for our steady aerodynamic analysis. We have 7 flow conditions at Mach 0.8 and the angles of attack of -2 degrees, 0 degrees, 2 degrees, 4 degrees, 6 degrees, 8 degrees, and 10 degrees. And these are specified by 7 flutter bulk data cards that are referred to by 7 flutter case control commands in the case control section. And we're just going to illustrate one case, which is the first case. So this will be the -2 degree case. So we have the case control command refers to the flutter card. The flutter card refers to an ST flow card, or rather the ST flow card has the same ID as the flutter. So the ST flow kind of refers to the flutter card. The flutter refers to the fix MATM, which refers to the MK Aero Z, which then refers to the trim flut card, which then refers to the viscous card. So our flutter card is here. Fix is 1 to refer to the fix MATM. So here we define the altitude here to be 0. So this is at sea level. Refer to the MK Aero Z card here. So we have Mach 0.8. And then we refer to the trim FLT card here with ID 1. So that defines our H-tail at -4 degrees. So that gives us our -4 degree deflection of the tail. So that will be our steady flow. And then the trim flut with refers to the viscous card with ID 2000 for the viscous analysis. If we go back to the MK Aero Z card, that refers to the MK param. So we're using mostly the default parameters, except we have 150 time steps defined here. And then our ST flow card has an ID of 1, which is the same as the flutter card. And we're setting save stop. So this means that we're going to save the steady flow solution and then terminate the subcase computation after the steady flow is computed. So that means we're not going to go on and compute the flutter analysis. We're just going to compute the steady flow and then move on to the next case. So all of these, let's see. Okay, the only one I didn't mention was the last bullet point here. The plot CP card refers to the flutter card for the steady CP display. And the plot CP is not shown here. Now we'll look at the output file. So in the output of each subcase, the most critical output that the user should pay attention to is the convergence history of the flow solution. So here we have the convergence of the lift coefficients after 151 iterations. So you can see this value's converging and then just stays flat. So this is good. And then we have convergence of the pitch moment coefficients. This also looks good. And after 150 iterations, the lift and pitch moment coefficients are well converged. And the force and moment coefficients at Mach 0.8, angle of attack -2 degrees, are printed out in the output file as shown here. So we can look at our normal force CL. That's in this table right here. And then we're printing out what our analysis parameters were. So you can quickly at a glance see, okay, Mach 0.8, alpha is -2 degrees, and these are the resulting coefficients. Now we'll look at the plot CP cards. So this is the pressure distribution. So we have the top surface and the bottom surface plotted, and we have -2 degrees, and then we have 4 degrees, and then we have 10 degrees plotted. For each of these plots, you can see our scale is different, so we've just got a best fit scale for each individual plot. So you can see here that the final CP display has been interpolated back onto the surface panel model, even though the computational model was the fuselage was the boxy thing that we saw several slides back. Also, you can see that even though in the computational mesh the C07 is kind of a flat plate, it does have separate boundary conditions for the upper surface and lower surface, and then the CP plot is shown on the thick model with the PA foil 7 effects. So the top surface and bottom surface of the wing, you can see the separate CP contours for the upper and lower surfaces. Next, we'll compare the ZEUS and the wind tunnel data. So Mach 0.8, that's where we set everything up on the previous slides. We're having a ZEUS inviscid analysis. Then we have the ZEUS viscous analysis. The ZEUS viscous is what we saw, and then the circles are the wind tunnel data. So here we have the normal force coefficients as a function of angle of attack. We have the pitching moment coefficients as a function of angle of pitching moment coefficient in versus the normal force coefficient Cn. So that's shown here, and then we have the normal force and the drag shown here. So for drag, we only have the ZEUS viscous results. Here you can see we've matched really well. And then we've gone on and also done the analysis for Mach 0.94 and 1.03. So the input would be similar, you just change the Mach number. So here we have normal force versus angle of attack, pitching moment versus normal force, and then normal force versus drag. Mach 1.03, normal force versus angle of attack, pitching moment versus normal force, and then normal force versus drag. So in all these cases, you can see that ZEUS is matching the wind tunnel data quite well. Okay, our next test case, we'll look at a steady hypersonic analysis of a bent nose compact kinetic energy missile called CKEM with 8 wraparound fins. So here is the ZEUS model. So the purpose here is to validate the lift and moment of a bent nose compact kinetic energy missile with 8 wraparound fins configuration at Mach 6.0 with the wind tunnel data. And we're going to demonstrate how to generate a 9-block overset mesh to model the CKEM configuration. So we have the missile body here will be the main block, and then the 8 fins, each fin will have its own block. So the side view, you can see how the fins here are in the back, and then the nose of the CKEM is bent. So we'll be looking at 2 cases, a 2-degree bent nose angle and a 0-degree bent nose angle, in other words, not bent. And then the straight-on view, you can see the fins. So the reason the fins are curved here is before the missile is launched, the fins are flush with the body, and then once the missile comes out of the tube, the fins pop out, so that's why they're bent. And then here's a diagram of what the fins look like. So each wraparound fin is modeled by 9 C07 bulk data cards. So that's how we get this changing dihedral angle. So this approximates the warped shape, and there are in total 8 times 9 C07 bulk data cards to model the 8 fins. So each fin is 9 C07s, and then we have 8 fins. And the body is modeled by a single body 7 bulk data card, and the bent nose angle is introduced in the camber line specified in the SegMesh bulk data card. So you can see we just have a simple body revolution and then the bent nose angle will be applied through the camber entry. So it's still a body revolution at each axial station, which we just have varying camber. Next, we'll look at the fins here. So the 9 CARO7 bulk data cards of each fin are located in a local coordinate system specified by an A-chord bulk data card where the dihedral angle of the fin is specified. So except for the identification numbers, the input data of the 9 CARO7 bulk data cards on each of the 8 fins is identical. So this reduces the input effort by quite a bit, because for each different fin, we just need to change the definition of the A-chord card, and then the CARO7s, everything else will remain the same. And then the airfoil sections of each fin are defined by 9 PA-foil7 bulk data cards, and all 8 fins refer to those same 9 PA-foil7 bulk data cards because the airfoil shape is the same. So if we just look at fin 1 here, the dihedral angle is minus 90 degrees, so the A-chord ID is 10, and then our 9 CARO7s are 1100, 1200, 1300, and so on, up to 1900. The 9 PA-foil7 cards are listed out here. And then the AE fat cards, which specify the airfoil thickness, the IDs are listed in this table. Next, we'll look at a single fin. So each fin is embedded in a block of mesh defined by a block card. Each block is located in a local coordinate system, and each block specifies 9 Y zones for the 9 CARO7s. So each individual CARO7, you can see that the end span is 3, so we just have 2 boxes for each CARO7, and then the Y zone is aligned with each of those CARO7s. And then, of course, we have 8 block cards for the 8 fins. Now, because of the local coordinate system, referred to by the block card, the entries X lead, X trail, Y left, Y right, Z bottom, Z top, YL, and YR are identical. And then each block refers to a mesh param card where the growth rate of the volume mesh from the surface mesh is specified. So as an example, our block with ID 1 is here, and then this is the mesh param. So we are altering the X growth, Y growth, and Z growth. And then our A chord reference is here. So the origin is always 0. We're just changing the angle that the block is rotated. So for the first one, we have the minus 90 degrees. And then our X lead is 35, X trail is 60, Y left is 1.107. So this is the diameter of the body. So Y left is going to be right at the root of the fin. And then 2.5, that's going to be up here somewhere. And then our Z bottom and Z top are minus 0.7 and positive 0.7. So that's going to be inside and outside the page here. So that's going to be above and below the fin. So the Y direction for each block is along the span-wise direction of the fin, and then the Z direction is normal to the fin. And then, of course, X is the flow direction. So now we got a head-on view here illustrating the blocks and the body here. So the values of Z bottom and Z top of minus 0.7 and positive 0.7 in each block are calculated so that the outer boundary of the mesh of each block projected on the YZ plane in the global coordinates does not intersect with the surface mesh of the other fin. Because if the surface mesh intersects with the other blocks of mesh, the hole cutting scheme cuts a hole near the surface mesh to avoid such an intersection, which we want to avoid. And the hole near the surface mesh decreases the solution accuracy. Therefore, it should be avoided, which we've done here. Furthermore, if we look at remember we use the outer 2 layers of cells, we'll interpolate the flow solution from the outer block or the parent block. So if we look at the outer 2 cells of this one here, and then the outer 2 cells of this one here, we can see that the interior cells actually do not overlap each other in these two blocks, which is also good. So the outer two cell boundary is here and right here. So they barely do not overlap each other if you just look at the interior cells. So a little bit of overlap is okay, but once you subtract the outer two layers from this block and the outer two layers from this block, the remaining cells actually do not overlap each other. Next, the growth rate of the mesh size from the surface mesh to the outer boundary is defined in the mesh param card. So X growth is 1.15, Y growth is 1.15, and Z growth is 1.15, except we have a negative Z growth. So the negative Z growth allows this block to follow the contour of the fin. So you can see the fin is bent here like this, and then you can see that the outer contour of this block follows that bent shape. If Z growth were to be positive, then the outer boundary of the mesh would just be a rectangular box. This rectangular box would be a little bit, it end up being larger, and it would be harder to minimize the overlap between adjacent blocks. And the number of grid points generated by each block is 24 times 25 times 27. Next, we'll look at the volume mesh generation for the center body. So the flow field mesh of the CKEM is generated by the block 1 bulk data card to generate a body-fitted mesh. And this body-fitted mesh provides a more accurate solution than the block bulk data card. So for this particular case, the majority of the aerodynamics we're worried about are actually the aerodynamics generated by the missile body itself, not the fins. Whereas usually in aeroelastic analysis, the wings are what is important. So we don't care as much about the body aerodynamics. But in this case, body aerodynamics dominate. So it is important to use this body-fitted grid. So the seg mesh card divides the surface mesh of the body into 60 axial stations and 129 circumferential points. The 65 radial lines in the 2D O-type mesh on each axial station originate from the 129 circumferential points, and along each radial line, 25 grid points are generated. So the block 1, the 25 here, means that we've got 25 grid lines out in this radial direction. The AE FAT card specifies the locations of the 25 grid points along each radial line in terms of percentage of the length of the line. So that's done here. So we use a very small mesh size near the center body, which is 0.25% of the total length of the radial line. That's the first size. So this keeps the center body mesh size in the overlapping regions to be compatible with that of the 8 wraparound fins mesh. And then the negative sign triggers the automated mesh generation scheme to also generate grid points inside the center body. Now, because the center body is a truncated in-body, flow separation occurs after the end of the body back here, and the grid points inside the body are used to model the separated flow. Now we want to look at the overset mesh. So it's extremely important to know that the overset mesh scheme requires the information of the overset strategy, that is the sequence of the blocks of mesh from the global mesh to the smallest embedded mesh, to be listed in the block sequence card. So if there's no block sequence card specified, then the default strategy assumes that the mesh generated by the block bulk data cards with the smallest identification number is the global mesh, and then the mesh generated by the block 1 card is an embedded mesh, which is incorrect for this particular case. So the default overset strategy would be incorrect. So the correct overset strategy for this case is to use the block sequence card. So in this block sequence card, which is shown here, the identification of the block 1 card is listed first. So the ID of the block 1 card is 100, so that's listed first. And then we have the 8 block bulk data cards, 1 through 8 are listed next, so we know that those are the smaller blocks. Then we use a block layer card to specify the layer numbers for each of these blocks. So the first block with ID 100, that's our block 1, the main block, that has a layer of 1. And then each of the 8 fins has a layer number of 2. So this tells Zeus that the 8 fin blocks with the layer 2 are embedded inside the main block with a layer number of 1. Furthermore, Zeus will enforce the condition that these fin blocks will not communicate directly with each other. Now, because the interior blocks do not overlap with each other, that wouldn't happen anyway, but we want to go ahead and specify this to have all of the 8 fins be the same layer number of layer 2. So that way they're directly embedded in the main block and then they do not communicate with each other. Now, if the embedded blocks had an overlapping region, then the embedded blocks could potentially communicate with each other. But since they have the same layer number, they do not communicate with each other. And then the overset mesh is visualized using the plot arrow card. So that's how we get this plot here. Next, we want to look at the IBLANK array. So this will show how the hole cutting scheme in ZEUS works. Now, usually you do not need to look at the IBLANK array. You can just kind of look at the mesh and determine that, okay, my overset looks reasonable. But if we're going to really dive in deep here to see how the interpolation between the blocks works so that you can be aware of it, so that you, as a user of ZEUS, can generate good overset blocks. So the overset strategy could potentially render a flow leakage problem if the mesh sizes between the global mesh and the embedded mesh and the overlapped regions are not compatible. So the flow leakage could occur here at the boundary between the fin and the body. So for instance, if a surface is physically attached to another surface, like we have here, the fin is attached to the body, and if these two surfaces belong to different blocks of mesh, which is what we have, such as the fin and the center body of the CKEM configuration, then the flow could pass through the root of the fin and create a non-physical vortex roll-up from the fin root. So in the main block, remember the fin is not modeled in the main block. So potentially we could just have the flow completely ignoring the fin and flowing through the fin. So to ensure that the flow leakage problem does not occur, for this case, we have a param card with name IBLANK shown here to create this file called IBLANK. So what this IBLANK file is showing is which cells are donor cells and which cells are receiver cells. So the donor cells, which we also call non-receiver, so the non-receiver cells are where the flow solution is computed in that block. And then the receiver cells, the flow solution is not computed, it's receiving the flow solution from a different block. So this is a 3D view of the non-receiver cells of a fin block. So these are the interior cells in the fin block. So at these cells, ZEUS will compute the flow solution. So it's kind of hard to see, but you can see right here, there's a little section jutting down from these other parts, and that is this section right here. So right here, these cells, despite being on the outer boundary of this block, ZEUS marks these cells as non-receiver cells. So ZEUS is computing a flow solution because they're adjacent to the fin. So that's this part here. This is where the fin is coming down and connecting to the body. So now when we look at this cross-sectional view, this is the fin block. These blue cells in here are the non-receiver cells. So ZEUS is computing the flow solution. These cells out here are the receiver cells. So they are receiving the flow solution from the main block. So at each step in the solver, these cells, the flow solution is not computed. It's interpolated from the main block, and then is held constant. And so in effect, this is the boundary condition for these interior cells. So these interior cells see the flow in these adjacent blocks, and then that becomes a boundary condition. Now, right in here, you can see that we have more than 2 cells that are receiver cells. And the reason for that is we have this body here. And so we have cells. Now we got to come over to this figure. We have 2 layers, or actually, is it 3? 2. We have 2 layers of cells in the main block, which are adjacent to this body. And these are marked to be non-receiver cells. And so these cells are always non-receiver cells. And so they are contributing the flow solution to the embedded block. So as you follow the curvature of this body, that's what's going on here. You can kind of see there's a curvature here. And so all of these cells are receiving the flow solution from the main block. Except in this region here where the fin attaches to the body. So now we have these, the cells are kind of fighting each other. These cells are close to the body, so they want to be donor cells. But then over here, these cells are close to the fin, so they want to be donor cells. So basically, whichever one is closest to its respective surface wins out. So we've got one grid point right here in the main block, which is marked as a receiver cell. So because this cell is closer to the fin than it is close to the body. So because this one cell right here is marked as a receiver cell and it's receiving the flow solution from the fin, that will prevent the flow leakage problem that we just talked about. So in other words, as the flow right here is close to the body and it wants to just flow freely along the body through the fin, it can't because there is just this one cell right here that is a receiver cell that's receiving the flow solution from the fin. So that prevents the flow from freely flowing through here. So basically, in the end, what does that all mean? Do you have to look at this picture every time you have this condition? No, I don't think you do. Basically, what you want to do is ensure that the grid density of the 2 blocks is similar where the 2 intersect with each other. So the grid density of the main block and the grid density of the fin block here at this intersection region, which is very small, it's just in this region right here, the grid densities are very, very similar. And so we get this situation which we have a good hole cutting result. And then as you move further away, you can see that up here, we actually have very large cells in this direction, which are much larger in this direction than the fin cells are in this direction. But that's okay because we're away from this junction. And so the sizes are still compatible. They're not exactly the same, but they're close enough to be okay. Finally, the last figure here, we have a 3D view of just the receiver cells in the global block. So in the global block, every cell that is not plotted here is a computational cell. But these cells here are the receiver cells. So these cells are not, will not be solved in the Euler solver. We simply will interpolate the flow solution from the fin blocks onto these cells, and then the solution's held constant, and it's used as kind of a boundary condition for the surrounding cells. So you can see there's this one little strip right here, which is representing the fin. That's this one right here. That's where the fin is attached to the body. Okay, and then you can ignore this gap. This is just a plotting artifact because of the way it's a radial plot, and so really these are connected. It's just it's not in the plot, so that's not a problem. Okay, next we'll look at the input for the steady aerodynamic analysis. So the steady aerodynamic analysis of the rigid aircraft must be performed by the flutter module. So we use the ST flow card with entry save equals save stop or acquire save stop to stop the execution after the steady flow solution is generated. And then we use the plot CP card to output a tech plot file for the CP display. We have 60 pseudo time steps, 4 Newton subiterations, and 2 Runge-Kutta pseudo time marching steps are specified in the MK param card, which is not, oh no, here it is. So we have the 60 pseudo time steps, 4 Newton, and then 2 end cycle, which is the Runge-Kutta. The Mach number of 6.0 is specified in the MK Aero Z card right here. The angle of attack is specified in the trim FLT card. So our angle of attack for this case is 0 degrees. And then we have a CFL number of 1.5 specified in the MK param card. That's right here. This is necessary for this particular hypersonic computational case. So remember the default CFL number is 7, but here we're specifying 1.5. And now we'll look at the results. So the steady CP at Mach 6, angle of attack 0 degrees, generated by the plot CP card is shown here. And then we have 2 configurations. We have a bent nose of 0 degrees and a bent nose of 2 degrees. And the ZEUS results are validated with the wind tunnel test data and also compared with the DATCOM results. And the CPU time for each angle of attack case is approximately 3 minutes with 8 CPUs. And this 3 minutes time, that was on a reasonably modern computer from about 2019. I don't know exactly what computer, but you know, a reasonably modern computer from 2019. So the test results are in black. The squares are the 0 degree bent nose and the circles are the 2 degree bent nose. So let's look at the 0 degree, so that's the squares, and then our ZEUS is the blue squares. So that's matching pretty well. This is CL versus alpha, and then the circles is the 2 degree, so that also matches pretty well. The CM, the pitching moment, that's a little bit harder to match. So the squares are the 0 degree, so of course at 0 degrees angle of attack, we would expect CM to be 0, and it is. And these are the results, and then for the 2 degree, that's up here. So you can see the experimental results are actually quite noisy in here. But then if we just look at the overall trend in the 0, 2 degrees angle attack, 4 degrees angle attack, and 6 degrees, ZEUS is doing quite well for both the 2 degree bent nose and then down here the 0 degree bent nose. And then the magenta down here, that's the DATCOM results, just for comparison. Okay, our next test case, we'll look at the steady and unsteady CP of an F5 with tip tank and underwing store. So the purpose here is to validate the steady and unsteady pressure coefficients with the wind tunnel data of an F5 wing with the tip tank, underwing store, and pylon configuration oscillating with a pitching mode at Mach 0.8 and a reduced frequency K of 0.176. And we're going to demonstrate how to generate a 2-block overset mesh to model the wing store configuration using 2 different approaches. So we'll look at 2 test cases here of the same model. The first approach will model the wing, the tip tank, as well as the pylon and a main block of mesh in which the pylon is treated as a vertical surface so that it can be fitted into the main block of mesh, whereas the underwing tank is modeled in an embedded block of mesh. So only the underwing tank, this right here, will be in the embedded block. Everything else will be in the main block. And note that this goes against the recommendation of putting a vertical surface, in this case the pylon, into the main block. So this is to illustrate that it is possible to do that, but we recommend against it, and so we'll see what that does. And then the second approach will model the pylon and the underwing store, so both of these components, in a block of mesh embedded in the main block, and the main block contains the wing and the tip tank. So this is the surface panel model. The wing is modeled by a single C07 bulk data card that divides the wing planform into 41 chordwise divisions and 28 spanwise divisions. So we have a total of 40 times 27 boxes. Now, because the leading edge of the pylon is curved, it must be approximated by several trapezoidal surfaces, and each surface is modeled by a C07 bulk data card. So we have 3 total C07 bulk data cards for the pylon. The tip tank is modeled by a body 7, and this body 7 refers to an A-chord bulk data card where the origin is at x equals 0 and then y equals 0.6646. So that's out here, that's along the center line of the tank, and z equals 0, and then a delta of minus 2.5 degrees. So the inclination angle of minus 2.5 degrees does not physically rotate the tip tank surface mesh. The inclination angle is introduced in the boundary condition to reflect the nose down angle effects of the tip tank. And then the underwing store is modeled by a body 7 down here. Now, because the wing and the tip tank can be fitted into one block of mesh, then the gap between the wingtip and the tank does not exist in the computational mesh. So we'll see that when we set up the Y-zones. When you look at the surface mesh, it looks like there's a gap, which of course you see, if you guys coming from CFD are not going to like that. But remember, in ZEUS, the body is actually modeled computationally as a body box. And so we'll see that the body box actually is watertight with the wing. And so computationally, there is no gap. Okay, next we'll look at the volume mesh generation for the first approach. So remember, in this one, the wing, the tip tank, and the 3 C07s for the pylon are fitted into the main block. And so here we can see this is the body box for the tip tank. So it's just a rectangular box here, and you can see it's flush with the wing. And then underneath here, the 3 C07 macro elements for modeling the pylon. Now these are forced to be vertical surfaces. They're not allowed to have a sweep angle because it's a vertical surface. So you can see that ZEUS changes internally the mesh just to be made up of these surfaces with no leading or trailing edge sweep angle. So they're just rectangular surfaces. The underwing store is modeled by an embedded block, so that one is down here. So this is the computational surface mesh of that body box. And then we use the plot slope card to generate this figure. So you can see the computational surface mesh along with the slope distribution. So with the underwing store, you can see here at the nose, we've got a slope, and then it's relatively flat. And then at the trailing edge of the store, we get a steeper slope again, where the store is getting smaller. And the same thing with the tip tank. Our scale is pretty large. You can just barely see the slopes in the interior region here, where the tip tank store gets smaller and then gets larger again. Furthermore, just based on the scale here, we can see that all the slopes are less than 1.5, and so no warning message will be printed out by ZEUS. Now we'll look at the overset mesh. For the first approach, the 2-block overset mesh generated by the first approach is shown here. So the embedded block here only contains the store, and we can see the boundary of it goes up to the wing right here, and then this is the top-down view. And then we use the param card with the parameter IBLANK to generate these the IBLANK, or the donor receiver cell plots over here. So the main block is up here. The white region in the main block represents the hole cut in the global mesh in which the embedded mesh for the underwing store model is located. So this is just a slice from the main block that's somewhere along the store, so it's probably like about right here. So in this, the white region here, the main block will not solve the flow solution. It will take the flow solution from the embedded block. The embedded block will contribute the flow solution back, and then the flow solution in these cells will be held constant while the Euler solver solves the remaining cells. Now you can see the pylon, because the vertical pylon is in the main block, we do have computational cells along the pylon here. So it kind of, this region here, without the pylon, this would all be white, but with the pylon, the main block needs to solve these cells. Okay, so now if we come down to the embedded block, because the pylon, okay, I just said that, included in the main block, this blue region here includes the wing and tip tank, and then also includes the 3 layers of mesh on the right and left-hand side of the pylon. And then the mesh near the wing pylon junction is completely sealed, through which the flow cannot pass to eliminate the non-physical vortex roll-up from the root of the pylon. So that's down here. And then this is the embedded block. Note that our 2-cell boundary around the edge is white, so we're receiving the flow from the main block, and that's being contributed to the embedded block. Additionally, because of the pylon, you can see this little part here is cutting further into the embedded block. So the embedded block will not solve these cells here. However, we do have 3 layers of cells adjacent to the body box of the store, which is right here. So the store boundary is right here, and then it comes up a little bit higher. There's 3 more cells where the embedded block will solve the flow solution. So then this little region in here, you can see that we're going to receive the flow solution from this embedded block. So these blue cells here, the Euler solver will solve the flow solution for the embedded block, and then the white cells, it's receiving the flow solution from the main block. Okay, now for the second approach, the wing and the tip tank are in the main block, and then the pylon and the underwing store are fitted into the embedded block. So this block, embedded block, is located in a local coordinate system, and we're going to rotate it 90 degrees so that the pylon and the underwing store lie on the XY plane of the local coordinate system. And so on this local XY plane, a sheared mesh can be generated to accommodate the swept leading and trailing edges of the pylon. So when we look at the computational surface mesh here, you can see that we've retained the leading and trailing edge sweep angles of the pylon. So unlike the first approach that approximates the 3 CEUS macro elements by 3 rectangular vertical surfaces, the second approach can model the exact plan form of the pylon, which is desirable. And then using the plot slope card, we've created this computational surface mesh. So we can see the slope distribution. Okay, moving on. Now we'll look at the overset mesh. Now the sheared mesh of the embedded block is transformed back to the global coordinate, rendering a 2-block overset mesh. So the blue here, this is just the embedded block, and then we've not plotted the main block, so otherwise this figure would be very cluttered. So you can see the mesh here is, we have the sweep angle of the pylon in the embedded block. And then once again, we've plotted the IBLANK array, which is the donor and receiver cells. Okay, so now when we look at the main block, the white area here is where the main block is receiving the flow solution from the embedded block. And then we have 3 layers of mesh in the embedded block on the right-hand side and left-hand side of the pylon are kept to prevent the flow from passing through the root of the pylon. So first, let's look at the embedded block. Once again, at the boundary, we've got 2 layers of cells in the boundary where we are receiving the flow solution from the main block, except we have the pylon, which goes all the way to the edge of this embedded block boundary. So we have 3 layers of mesh on each side of the pylon, which are forced to be non-receiver cells. So the Euler solver will compute the flow solution for these 3 cells on each side of the pylon. So now when we go back to the main block, you can see how these cells here kind of cut in right here, and so we're receiving the flow solution from the embedded block in the main block here. So you can use this IBLANK array, and this creates a plot file in the plot3D format, and TechPlot can read the plot3D file format, so we're using TechPlot to view these results. So when you do this, you can ensure that the overset mesh does not introduce the flow leakage problem, as shown here. So basically, if these cells up here were not white, if they were all blue, then you would have cells underneath the wing where the flow can just freely pass through the pylon, because remember, the pylon is not in the main block. So we want to make sure that we've got these few cells here that we're receiving the flow solution from the embedded block to model the effect of the pylon so that the flow cannot pass through the pylon. And I should note that you don't have to pick which cells. This is all automatic. It just depends on the grid density and, you know, are you modeling the blocks correctly. So in the case of the embedded block, the boundary comes right up to the edge of the wing, and then we've ensured that our grid densities are similar, especially in this region here between the main block and embedded block. So as long as the grid densities are compatible, then you should have a good overset definition. And so you can just use this plot file to verify that. So next we'll look at the steady CP comparisons between the two approaches. So we'll use the plot CP card. The CP distributions on the wing lower surface along span stations 1, 5, and 6 at Mach 0.8, angle of attack 0 degrees, and Reynolds number 18 million are shown here. So we have the first approach, which has the vertical pylons, rectangular surfaces, and the second approach is where the pylon is with the store. So station 1 is well inboard. That's right here of the store. So the two the two results agree quite well, both with each other and with the test data. So the test data is in the open symbols. ZEUS is the solid line. Now station 5 is just inboard of the pylon. So you can see that both approaches actually do pretty well, and we're plotting both with and without the store. I should have mentioned that. So the blue is with the store and the red is without the store. However, both do have the pylon. And then station 6 is just outboard of the pylon. And it looks like to me that our second approach is doing slightly better. So the results are different when you look at this line compared to this line. If you look at the experimental results, so obviously the experimental results are the same in both figures, you can see the difference here. So in the second approach, remember the pylon is in the embedded block, whereas in the first approach, the pylon is in the main block. And the CP on the wing is coming from the main block. So the aerodynamic influence from the pylon and the underwing store to the wing can be seen by comparing the wind tunnel data measured on the clean wing and on the wing with the pylon and underwing store. So the aerodynamic influence can be captured by both the first and the second approaches. And then except the second approach results are slightly closer to the wind tunnel data than the first approach. So once again, we're just recommending that if you have a vertical surface, then it should be put in its own block, where in that block it becomes a horizontal surface, so that the sweep angle is accounted for correctly. Next, we'll look at the unsteady CP comparison between the two approaches. So this will be station 1, so this is well inboard of the store and pylon. So the frequency domain unsteady CP due to the pitch mode is computed by the linearized Euler solver. So on the left here we have the real CP, on the right we have the imaginary. So this is the first and the second approaches, and you can see that they both agree quite well with the test data. Moving on to station 5, we've got the real CP for the first and second approach, and then we've got ZEUS in the red and ZEUS in the blue. So so we can compare both to the wind tunnel data and to the ZEUS data. And then we have the imaginary on the right. So it looks like ZEUS is matching the experimental data a little bit better than ZEUS for both the first and the second approaches. And then we'll come to Station 6, just outboard of the pylon. So we have the first approach and the second approach. And once again, ZEUS is doing better than ZEUS. Okay, let's go to the next test case. Here we have a frequency domain flutter analysis of a twin-engine transport flutter model. So this particular flutter model was tested in the transonic dynamics tunnel with heavy gas between Mach 0.77 and Mach 0.82. Two flutter modes were found, so that's in this region down here. The wing nacelle mode, which is around 17 hertz. Okay, so that's this mode, flutter mode, and then the wingtip mode, which is 22 hertz, which is up here. Now in this lower Mach number region right here, the wing nacelle mode has low unstable damping. That is, it's a hump mode. And so when they did the wind tunnel test, instead of being explosive flutter, this was very benign, and so they encountered LCO. And so the test engineer was comfortable to continue to raise the dynamic pressure, even though we have an unstable mode, because due to the nonlinear damping effects, it only developed into LCO. It was not catastrophic flutter. So they were able to continue increasing the dynamic pressure without damaging the model, and then they encountered the wingtip flutter mode, and then they terminated the test here. So that's why in this region we have two flutter modes from the experimental data. I mean, usually from experimental data you'll only see one flutter mode, but in this case we were able to capture two. However, beyond Mach 0.82, so from here onwards, the unstable damping of the wing nacelle mode became too high, which could lead to the destruction of the flutter model, which of course we don't want. Thus, the wingtip flutter mode condition could not be reached, and so they terminated the test. They stopped increasing the dynamic pressure after they encountered the wing nacelle mode when the Mach number was greater than 0.82. So we just have these test data points. So we're going to do this analysis in ZEUS to see how well we can compare with the wind tunnel data. So here we've got our fuselage, which is a body 7. And then in the body 7, we're going to disable the generation of the horizontal Y-lines on the YZ plane from the body 7 because we have a wing as well. So we'll use a gap Z card to control those Y-lines. Then we've got an engine nacelle, body 7 card. We have 3 C07s for the pylon. We've got 2 C07s for the inboard wing, and then 3 C07s for the outboard wing. So now we'll look at the model here. So this is the top-down view, so you can see the fuselage and the wing. And then here's the gap Z that I was talking about. So the gap Z is used to improve the mesh smoothness in the Z direction. So we had the minus sign in the NSEG entry for the body 7, which we saw in the last slide. So that's necessary to disable the generation of grid lines due to the fuselage cuts. So the gap Z adds these additional Y lines in the Z direction. So we get a nice smooth mesh between the wing and the fuselage. Additionally, because we've got the fuselage ahead of and behind the wing here, we added some gap cards to control the spacing so that we get a nice smooth mesh. So from the wing, you can see that at the root, our mesh size is a little bit larger, and then at the tip, the mesh in the chordwise direction becomes smaller. So we use the gap cards to have that same condition in the volume mesh ahead of and behind the wing. Without the gap cards, the X length in the chordwise direction is held constant across the wing, when we're coming away from the fuselage. So with the gap cards, we can make the mesh smaller and smaller and smaller as we go out towards the tip, so that we've got a nice, smooth, consistently varying mesh size out at the tip. So our block 1 card is here. We've got 6 Y zones. So the first Y zone is just the fuselage. The second and third Y zones, we've got 2 CE07s on the inboard wing. Then we've got the vertical pylon and engine nacelle, which is not shown here because that will be in a separate block. And then we've got 3 more Y zones with 3 more CE07s. So for the first Y zone, we just have the fuselage. So the body 7 was ID1. The second Y zone, we have the CE07 of the wing. And then we've got the gap ahead of the wing. We've got the gap card behind the wing. And then we have the gap Z card. And then we just carry on for each of the Y zones where we've got the CE07 and the gaps in these Y zones. Here are the gap cards defined. And then here's the gap Z right here, which defines these the Z spacing. Additionally, you can see we've got the mesh parameter card to have different growth rates. The default is 1.3. So for the X growth, we've decreased that to 1.2. Y, we've kept at 1.3. And then Z, we've changed to 1.25. Now we'll look at the engine nacelle. So we've got the body shrinking option on Z bottom and Z top. That's activated to avoid or minimize the portion of mesh above the main wing. So this engine nacelle, the top of it is very close to the wing. However, it is out ahead of the wing. So in this block of mesh, we want to minimize the number of boxes that are up above the wing. Because if we have boxes above the wing, remember we just use the outer 2 cells of this block to interpolate the flow solution from the main block. So if these outer 2 cells are above the wing, but then the remaining cells are below the wing, that's nonsensical results, because now we're having flow above the wing, which is determining the boundary condition for the block, but then the remaining cells for the block are underneath the wing. So we want to try to push all of these cells to the underside of the wing so that the interpolation is correct. So we accomplish that by using the shrink option so that the body box isn't just determined by the top of the nacelle, rather the box follows the contour of the nacelle so that we curve this down so that it can go underneath the wing. So we use the ZT, ZB, so we shrink both on the top and the bottom. Then we've got a P-body 7 card to specify the flow-through condition of the engine nacelle surface panels. So in the very first station here, these boxes we want to be inlet boxes. So we refer to the ID of all these boxes, and then we specify 100% flow-through. So these boxes all have 100% flow-through. So there won't be any force on these boxes. Okay, next we've got a block of mesh for the engine pylon. So to model the vertical pylon as a horizontal surface so that the mesh follows the sweep angle, we use a local coordinate system to rotate it by about 90 degrees. And then the Y left of the block is at the root of the first CE07 so that the block of mesh won't extend above the main wing, which is the most critical component. So here we don't have this block penetrating above the wing. It looks like it goes above just a little bit, but once we interpolate the outer 2 layers, it will be, that second layer is below the wing, so this is close enough. Another option, instead of rotating this block a full 90 degrees, you could rotate it just a little bit less so that it's actually perpendicular to the wing instead of being aligned with the pylon. So in that case, if the block is aligned with the wing, then the pylon would have a slight dihedral angle, which is fine. That doesn't matter. So either or. In this case, the dihedral angle of the wing is small enough where we can just have this block rotated a full 90 degrees, and it doesn't penetrate too far above the wing. And then these are the CRO7s of the pylon. And then here's the side view. You can see the block for the pylons. So now this is the total 3-block overset mesh. We've got the 3D view. Here's the YZ view from behind, the XY view up from above, and then the XZ view from the side. So the block 1, we've got 112 times 50 times 61 cells. Block 2, we've got 32 times 35 times 39 cells, and then block 3 is 60 times 17 times 25. Whoops, okay, sorry about that. We're a little delayed. Okay. Next, we've got the spline input. So for all of the CRO7s, we've got the spline 1, so the plate spline for both the wing and the pylon. For the fuselage, we have the spline 0. So the fuselage was just rigidly attached to the wind tunnel wall. It's kind of a fairing. So the fuselage actually doesn't move. So we use the spline 0, the 0 displacement spline. The nacelle, we've got spline 3. So we've got enough grid points out here so that we can do the 3D spline. And then here we've overlapped. This is the plot arrow card. We can plot the structure grids and the aerodynamic model together. So we've ensured that the two are aligned correctly. And then we've looked at the using the plot mode card, the interpolated mode shapes on the aerodynamic model. So here we've got mode 1, mode 2. You can really see the wing nacelle mode here in modes 2 and 3. And then mode 4, we've got a nice wing bending mode here. So by comparing these modes to the Nastran modes, we can ensure that we've done the correct mapping. So you would want to look at the Nastran mode, because for mode 2, you look at this engine and you think, oh, this engine's just kind of doing its own thing. The wing is relatively undeformed. But if you go back and look at the Nastran mode shape, this is what the engine is doing. So this is a correct mode shape. Next, we'll perform the frequency domain flutter analysis. So the computation of the generalized aerodynamic forces for 12 modes and 8 reduced frequencies at 1 Mach number takes 6 hours using 8 CPUs. And our reduced frequencies here are 0, 0.1, 0.2, 0.4, 0.6, 0.8, 1, and 2.0. And we have 2 sets of gaffs generated. The first is the jig shape without the static aeroelastic effects. So this will use just the flutter module of ZEUS. So the steady flow is calculated based on a rigid structure. So that's what we mean without static aeroelastic effects, and it's called the jig shape. And then secondly, we have the cruise shape. So the gaffs are based on the statically deformed shape. So in this case, we'll use the GenGaff module so that we can specify a dynamic pressure for the steady flow. So that will allow the structure to deform. And then the flutter boundary is calculated using the G method. So we'll look at the steady flow solution here. So the steady flow solution is saved on a file by using the ST flow card. And the saved steady solution will be imported for the flutter analysis in a later stage. So here we've got the it's the GenGaff subcase, and then we've got the ST flow ID matches the GenGaff ID. So the GenGaff is used to generate the steady flow solution only. SID is less than 0, so that's right here. ID surf is none, so we do not have any control surfaces, and then the W is for the gust, that's 0. So this disables the unsteady gaff generation for the FEM modes, the control surface modes, and the gust modes. So normally the GenGaff will calculate the gaffs for the normal modes, the control surface modes, and the gust mode. However, by specifying the negative sign, we disable the gap generation for the normal modes. And then when ID surface none, we have no control surfaces, so there's no gaps to compute. And then gust here is 0, so we won't compute any gust mode gaps. So the sole purpose of the gen gap here is to calculate the steady flow. And then our dynamic pressure, Q infinity, is 0.875. So this means that the structural deformation is considered, and the steady solution is based on the cruise shape. However, if Q inf or Q infinity was set to 0, then the steady solution obtained is on the rigid jig shape. So this particular input is for our cruise shape solution. And then in the MK param card, we've changed gamma. So the default value of gamma is 1.4, which is for air. However, this wind tunnel test was set in heavy gas, where gamma is 1.133. So we set that here in the MK param card. Let's see, what else is important? The gen gap refers to the MK Aero Z card, so that sets our Mach number, and then the MK Aero Z refers to the MK param, where we modified gamma. The MK Aero Z also defines our reduced frequencies, which isn't used here in the gen gap, but that will be used in the flutter analysis. We use the trim flut card to refer to the viscous, so we can set the Reynolds number. And then also we set the angle of attack to -2 degrees. So that's in the trim flut card. Next, we've got the steady aerodynamic results for 4 different Mach numbers, angle of attack -2 degrees. So we have both the jig shape and the cruise shape plotted here. So we use the plot CP card to generate the surface steady pressure data file. So with the jig shape and the cruise shape, you can see how large of a difference we have in the surface CP. So this makes a really large difference once we include the static aeroelastic effects, which is done in the cruise shape. So the jig shape analysis is going to be incorrect, because here we're assuming the structure is rigid and we're performing the analysis. So you can see how strong the shock is, especially at these higher Mach numbers. But when we go to the jig shape, we allow the structure to deform. And then when we generate the steady CP based on that deformed structure, you can see the shock looks a little bit weaker. So we would expect, once we get to the flutter results, we would expect the flutter results to be different between the jig shape and the cruise shape, where once again the cruise shape would be the correct analysis. So next we'll set up our flutter analysis. Let's see, so subcase 1, we've got the flutter here. So the steady flow solution is imported by using the ST flow card specifying acquire. So now the flutter module will not compute the steady flow, it will just import it from this file. So this is from the previous GenGAF module for the cruise shape. So the ID number of the ST flow matches the ID number of the flutter card. The flutter card refers to the fixed card. This is the fixed Mach, so this sets up our density and velocity. Well, this is where we'll perform the flutter analysis. And then the fixed Mach refers to the MK Aero Z, which defines our Mach number. And then this refers to the MK param, where once again we're changing the gamma. And then method equals 3 in the MK param. So that triggers the linearized Euler solver to be used for the gap generation. So then we've got the MK paral card to modify parameters for the linearized Euler solver. So we've set the CFL number to 3. Once again, gamma is 1.133. And then we're using 80 pseudo-time steps for the linearized Euler solution. Now for this case, the linearized Euler solver needs to use a CFL number of 3. So the residual smoothing has been turned off here. Now we'll look at the flutter solutions. So we've used the plot VG card to output the damping and frequency versus dynamic pressure. So let's see. we've got both the cruise shape and the jig shape plotted together. So this is the damping is the top row, the frequency is the bottom row, and then we've got our 4 Mach numbers in the 4 columns. So the cruise shape is the colored symbols, and then the jig shape is the black and white. And then our mode 1 are the squares, and mode 3 are the circles. So at Mach 0.796, both the jig shape and cruise shape give very similar results. They're almost identical. But then as we start increasing the Mach number, the cruise shape and jig shape results start diverging. So in the extreme case, if we come all the way up to Mach 0.88, let's see. So if we look at the circles, that's the mode 3. So the jig shape, that's the black here. The flutter boundaries way out here at about 170, 180 PSF. But then the cruise shape is all the way back here at about 130, 140 PSF. So that's a large difference. And then when we look at mode 1, which was actually the second flutter mode, the cruise shape is way out here at about 250 PSF, but then the jig shape is all the way back down here at about 190 PSF. The frequencies are pretty similar between the cruise shape and jig shape, however. So especially at Mach 0.88, you can see that the difference between the jig shape and cruise shape is quite large. Up to about Mach 0.85, the results are still pretty similar. Okay, now let's look at our flutter animation. So here we can see the wing nacelle mode, and this was generated using the plot flut card, so we can view the flutter mode. And then this is the wingtip mode. Once again, we use the plot flut card. So this allows you to view what the mode looks like. Okay, so now we want to correlate the ZEUS flutter boundary with the test data to see how well ZEUS did. So as we've just seen on the previous slides, the static aeroelastic effects have a strong impact on the flutter boundary at the higher Mach numbers. Now we've also plotted the CFL 3D solution. This requires 4,000 CPU hours for each Mach number, whereas ZEUS just took 48 CPU hours. And then both ZEUS and CFL 3D overpredict the flutter boundary of the wingtip mode. Now, according to Hong et al., this is probably due to the wind tunnel wall effects. Additionally, the static aeroelastic analysis is performed at the flutter dynamic pressure of the wing nacelle mode, not the wingtip mode. So remember, when we compute the steady flow, we specify the dynamic pressure. But then when we do the flutter analysis, we perform those computations at a range of dynamic pressures. So in reality, the damping and frequency that you get from the flutter analysis is really only 100% valid at that specific dynamic pressure at which the steady flow was computed. So what you can do is you can go back and redo the steady flow analysis but a different dynamic pressure, do the flutter analysis, and then extract the frequency of damping at that particular dynamic pressure at which that new steady flow was performed. However, there is a range that the flutter result analyses will be mostly correct. So if you just choose the first flutter mode dynamic pressure and use that as your steady flow, then your results will be pretty valid. We're just noting that here that could affect the results a little bit. So if you're really interested, you could go back and redo the analysis using that different steady flow dynamic pressure. So when we look at the results here, the wind tunnel results for the wing nacelle mode are the diamonds here. The ZEUS cruise shape is the solid circle with the solid line. So you can see we've matched that pretty well here. And then the jig shape is the dashed open circle. So once we get above Mach 0.86, that's where the results start to diverge. So we want to use that cruise shape. And then if we look at the wingtip mode, remember in the wind tunnel test, they were only able to test up to Mach 0.82, whereas in ZEUS, we can go ahead and continue increasing the Mach number to see the results. So like we said in the notes here, we did over-predict the dynamic pressure by a little bit. Okay, moving on with the next ZEUS test case, we have the Boeing joined wing trim analysis. So the Boeing joined wing has 6 trailing edge control surfaces on the front wing and 6 trailing edge control surfaces on the rear wing. And this is an ideal case to demonstrate the overdetermined trim capability of the trim module that can solve the optimal deflections on these control surfaces to satisfy the trim condition while also minimizing the sectional loads. And the trim condition to be satisfied in this case is a 2G symmetric pull-up at Mach 0.85 at an altitude of 55,000 feet. And the objective function to be minimized is we want to minimize the wing root bending moment. So we take the right wing root bending moment squared plus the left wing root bending moment squared. And obviously we square the quantity so that we can ignore the sign of the bending moment. And the constraints here are the deflection angles of all of the control surfaces must be within plus or minus 10 degrees. And this is the surface mesh. We have 32 CAERO7 bulk data cards to model the front wing. So this is the front wing here. We have 22 CAERO7 cards to model the rear wing. And we have 1 Body 7 bulk data card to model the fuselage, shown right here. And we have a P-Body 7 to specify the inlet panels right here. We have 2 CAERO7 bulk data cards to model the tail boom, which is right here. And then we have 3 block bulk data cards to generate the overset mesh. So the first block contains the front wing and the fuselage. The second block contains the rear wing, and the third block contains the tail boom. Next, we've got triangular panels which are required to model the control surfaces. Now, because the side edges of the control surfaces are not parallel to the x-axis, we have triangular panels to model the control surface. So this black line right here is the edge of the control surface. This is a blown up picture of this area. So you can see that the edges of the control surface are not parallel to the x-axis. So we have 2 choices. One, we could just approximate the control surface and say that this line right here is the edge. And the other option is to try to model the control surface exactly. And so we've demonstrated how to do that here. So what we do is we create these triangular panels so that these panels over here belong to the inboard control surface, and then these panels out here belong to the outboard control surface. So if we just take a look at this single CAERO7 right here, you can see that these panels right here belong to the inboard control surface, and then these panels belong to the outboard control surface. And the way that we create these triangular panels is we specify custom chordwise cuts for this CAERO7 right here. So if we take a look at the inboard edge of this CAERO7, we can see that we have the cut specified along the wing, and then at the end we have the 100% repeated several times, so that all of these cuts of the CAERO7 all terminate at the 100% of the chord line on the inboard edge of this CAERO7. And then for the outboard section, we have several cuts of the CAERO7 all come together at this 81.815%. So now when you combine these two, we get these triangular panels like this. So we have the same cut location for the 7 chordwise cuts. So we've got, on this side, we've got 1, 2, 3, 4, 5, 6, 7. And then on the this side, we've got 1, 2, 3, 4, 5, 6, 7. So this generates the 6 triangular panels on each control surface. And then in total, we have 12 AEsurf-Z cards to define the 12 control surfaces. We have 3 control surfaces on the right side leading wing. We have 3 control surfaces on the aft wing on the right side. And then, of course, on the left side, we have 3 and 3 again. So next, we're going to use the AES-LINK card to link 2 of the control surfaces, one on the right-hand side and one on the left-hand side, to come up with the symmetric control surface deflection. Now, because this is a full span model, the type of control surface is asymmetric, but we can see visually that the effect of the control surface is a symmetric deflection. So we've named these Sim FW1, so that's forward wing 1, Sim FW2, and Sim FW3. And then in the back we have Sim RW1, Sim RW2, and Sim RW3. So the way we define that with the AES-LINK card is we just link these 2 individual control surfaces. The scale factor to both of these is +1, so that a deflection of the Sim FW1 control surface will deflect these 2 physical control surfaces, resulting in this symmetric control surface deflection. And then we have 6 plot surf cards to create these 6 plot files. And I always recommend using the plot surf card to plot your control surface, to check to make sure that your hinge line has been defined correctly so that the control surface deflection is as you expect. And then also you can double check to make sure that the sign of the control surface is as you expect. So for example, if this left-hand side control surface, if we had defined the z-axis in the opposite direction, and then we have a positive deflection and it's going in the wrong direction, then you could see right away that actually this would be an anti-symmetric control surface rather than a symmetric. So using the plot card, we can visually verify that the control surfaces deflect in the direction that we expect. Next, we've got the block of mesh for the fuselage and the front wing. So first, let's talk about these triangular cells that we have in the wing. So the cluster of triangular grid cells merges the chordwise Y lines into a bundle of grid lines, forming 0 volume cells along the bundle of grid lines. Now the Euler solver can handle these 0 volume grid cells provided there are at least 5 grid lines in each bundle. And we have 7, so that's okay. And the Euler solver will automatically turn off the residual smoothing, and then additionally it will reduce the CFL number by half if you've defined the CFL number to be greater than 4. Next, we have a gap card used to control the grid cell size in the region behind the trailing edge. So that's back here. So the grid density here is comparable with that of the mesh of the rear wing as a result. So what we've done is defined a gap guard which just has a pretty much constant chordwise spacing rather than allowing ZEUS to automatically grow the mesh size. And that's done so that the mesh size in the main block is similar to the mesh size in this trailing wing block. Only one gap card is used on either on the right or the left hand side is sufficient. So ZEUS will mirror the left hand from the right hand, so you only need the gap on one side. Next, we have a gap Z defined because we've got a wing and fuselage junction. So we have 4 gap Z cards to control the grid spacing near the wing surface. So nseg is set to -1 in the body 7. And once again, you only need the gap Z on either the right or the left hand side. But in this example, we've just put gap Z's on both sides. So the first horizontal Y line above or below the wing is selected from either the one defined by the DZ fact in the mesh param card or the gap Z, whichever gives the smaller grid spacing. So normally what I do is I'll calculate what that the first gap Z in the wing is, which is based on the DZ fact and the ref C. And then in my gap Z, I'll go ahead and redefine that exact same location in the gap Z. Or you could just leave it blank in the gap Z and then the wing would provide that first cut. It's your choice. So here's the block card. You can see that we have several Y zones. That's the most Y zones that I've ever seen for a test case, and that's because we've got so many C07s out here. So every time we got a new C07, we have to have a new Y zone. So this Y zone right here, that's for the body or the fuselage, and then the gap Z's are in these two Y zones. So the very first Y zone to the left of the fuselage, the very first Y zone to the right of the fuselage, you can see that we've got these gap Z's. And then we also have the gap card right here. So that's in the first Y zone to the right of the fuselage. Next, we've got the rear wing block. So similar to the front wing, each cluster of triangular grid cells merges the chordwise Y lines into a bundle of grid lines, forming 0 volume cells along the bundle of grid lines. And then we've got, so starting at the left-hand side, this is our Y zone over here, and then we move all the way to the right-hand side, and then this is the wingtip out here. So this is the last Y zone on this side. Now we've used the mesh param card to modify the mesh parameters. So we've set X growth to minus 1.01. So we've decreased the X growth to keep the mesh size, to keep it from growing, and that's so that this mesh will be a comparable size to the main block. And we accomplished the same thing in the main block by using just a gap card. But because this is an embedded mesh and we don't need it to grow very far, we can just set the growth rate to 1.01 and only have it grow out to this far. And then we have the negative sign so that the boundary of the block follows the contour of our C07s that we have. So you can see the C07s are shaped like this, so then the boundary follows that same shape. If we had a positive sign, this would be forced to be a rectangular block, and then we would have highly skewed blocks in here, and then the volume cells in this region would be much larger, and these would be smaller like this. So the negative sign helps keep a consistent volume cell size. The Y growth, we've decreased the default from 1.3 to 1.05, and then the Z growth, we've changed the default from 1.3 to 1.08, and additionally we have the negative sign, so that in this Z direction also you can see that the dihedral angle of this wing is mirrored out in the outer boundaries of this block of mesh. So this minimizes the overlapping region around the front wing surface mesh. So usually with embedded blocks, I'll end up using this negative option for X and then also maybe Z, so that it ends up creating a smaller total volume block so that our overset region is smaller. And then we have the tail boom. So to model the tail boom as a horizontal surface, we've rotated this block by 90 degrees. So we have an A-chord card here, which we're rotating by 90 degrees. So now the block refers to that A-chord card. And then we've also modified the growth parameters for this block as well. So we have a negative value in the X growth so that this is the resulting shape of the block of mesh, so that we follow the sweep angle on the leading and trailing edges in the block. And then this is the front view, so this is how big our block is. So now we've got the 3-block overset mesh. This is the 3D view, and then you can see both of the rear wing block and the tail block embedded inside the main block. So in the main block, we've got 154 times 163 times 57 cells. And then in the rear wing, we've got 69 by 117 by 28. In the tail boom, we've got 25 by 26 by 29. Next, we'll move on to the trim input. So here we've got 9 trim variables, alpha, thick cam, Q rate, and then our 6 control surfaces. We set our constraints for all of the control surfaces. We have plus and minus 10 degrees. For alpha, we've also restricted that to plus or minus 10 degrees. And then we have initial values for the overdetermined trim set out here. Now in the trim card, we have the total weight is specified right here. The trim card is referring to the MK Aero Z card with ID 85. Our dynamic pressure is 0.6736. And I believe this is PSI because our model units are inches. Now, the given trim variables are thick cam, which is set to 1. So that's right here. So the trim var with ID 2 is thick cam, so we've set that to 1. Q rate, we've set to 2.82 times 10 to the minus 4. So let's see, that one's right here. So the trim var 5 is Q rate, and that's our given value. And then we have the free trim variables. So alpha is 1. So if we find the 1 right here, that's free. And then our control surfaces are in the 400s. So we've got the 401 free, 403 free, 405 is free, 407 is free, 409 is free, and 411 is free. Those are the 6 control surfaces. And then we have 2 trim degrees of freedom. NZ is 2 Gs. So in the trim card, the type or the acceleration units are in Gs. So NX and NY are both none. NZ is 2 Gs. And then Q dot we've set to 0. Now this is an overdetermined trim system because the number of free trim variables is 7, and that is greater than the 2 trim degrees of freedom. So because we have an overdetermined trim system, we are referring to the objective function right here with ID 777. So that refers to the trim OBJ bulk data card. So here's the trim OBJ, the trim objective card. So our objective function is 2.81 times 10 to the minus 5 times the right front wing root bending moment squared, and then plus the 2.81 times 10 to the minus 5 times the left front wing root bending moment squared. Now in this case, we've got this 2.81 just for our units, but since we just have these 2 values and they have the same coefficient, we could just change that to 1 and it wouldn't change the results. But this is just so we can have the units we want in the objective function. The trim function card with ID 213, that's the right front wing root bending moment, so that's down here. So we have the trim function card referring to the load mod card. So this load mod card defines the right front wing root bending. So we have the chord 2R to specify the x-axis at the root of the right wing. Then we have the pan LST3 defining the boxes, and then the set 1 defining all of the grids. And then in the trim OBJ card, we're taking this trim function value and squaring it. That's what this 2 is for. And then multiplying by that coefficient. And then we have the same thing for the left wing. We have the trim function for the left wing, and then we have the load mod card to define the component load. Next we have the MK Aero Z card. So this specifies the Mach number of 0.85, that's right here. And then it refers to the MK param card. We're using the linearized Euler solver, so that's what the 3 signifies here. So this MK param refers to the MK paral to set up parameters for the linearized Euler solver. Back on the MK param, we have 150 pseudo time steps to compute the mean flow solution for the trim variable thick cam. Even though ZEUS automatically turns off residual smoothing, we're also setting that in mkparam kind of for self-documentation. And then the CFL number, we've set it to 3. Because we've turned off residual smoothing, we need a smaller CFL number to achieve convergence. And then for the linearized Euler solver, we're just specifying 50 pseudo time steps to compute the aerodynamic stability derivatives for the remaining trim variables. And now we'll look at the ZEUS output file. So the mean flow solution is also used by the linearized Euler solver as the steady background flow solution. So here's the steady background flow solution. We have the convergence of the lift coefficients for 150 iterations and the convergence of the pitch moment coefficients. So you can see this is converging. You could also look at the residual values to ensure that they are decreasing by about 4 orders of magnitude. And then we move on to the linearized Euler solver. This example, or this portion of the output file is just for the trim variable sim fw3. So generally we want more than 2 orders of residual reduction in the linearized Euler solver. If we look at time step 1, this is our first residual. And then if we go to the end at time step 50, this is the last step. And you can see we've dropped to 0.2 times 10 to the minus 8. So here we've got about 2.5 orders of magnitude drop in the residual. So note here that we're being careful to look at the residual for block 1. So we have 3 blocks. So this is block 1. This is also from block 1. And then the residual here for block 2, you can see is much smaller. Block 3 is much smaller as well. So when we're comparing, we want to make sure we're grabbing values from the same block. Then we'll look at the stability derivatives and just compare those with ZEUS. So our thick cam, if we look at CL naught, ZEUS we're getting 0.8, ZEUS about 0.75, CM naught, ZEUS is minus 1.26, ZEUS is minus 1.11. Alpha, if we look at CL alpha, ZEUS gives us 0.2, ZEUS 0.2. CM alpha, we've got minus 0.39, ZEUS is minus 0.35. And then we have the 6 control surfaces as well. And then we'll look at the trim solution. So our constraints of plus or minus 10 degrees are satisfied. Once again, our constraints actually can be busted by a very small amount just due to the trim algorithm solver that we have in ZEUS. So if you have very hard constraints, I would recommend just setting your constraints to be slightly smaller, and then that way that gives a little bit of play so that the ZEUS trim solver can exceed your set limits by a little bit but still be underneath the hard limits. But we consider the 10.02 still to be satisfied, even though the constraint was 10. So you can see that the outboard forward wings are deflected a full 10 degrees, and then the outboard rear wing is also deflected a full 10 degrees in the negative direction, and then alpha is positive 6 degrees. So what's going on here? Remember that our objective function is to minimize the wing root bending moment. So in order to do that, we want to get as much lift as possible on the inboard portion of the wing, and then decrease the amount of lift that's coming from the outboard portion of the wing. So we do that by increasing the angle of attack and then deflecting the control surfaces out here on the outboard portion of the wing in the negative direction to unload the lift out here. And then we can use the plot trim card to view the deflection. So I believe this has been amplified. So you can see this deflection or bending in the wing here, and then you can also see the control surfaces deflected too in the plot. Next we'll look at the pressure contour. So we can use the plot trim card to output the CP and then also the deformed aerodynamic model. So the red here is the deformed shape, the blue is the original shape, and then this is the pressure contour on the aircraft. And then note here, the inlet boxes, the CP is just 0 because we have 100% flow through. So now, in order to show the reduction of the wing root bending moment due to the optimal control surface deflections, we also perform a determined trim analysis. So in this case, we create a control surface called SIMRAL, which links all 6 control surfaces on the rear wing together using the AES-Link bulk data card. And then we have 2 trim variables, alpha and SIMRAL, to satisfy the 2G symmetric pull-up condition. So in this case, the trim solution is alpha is about 5.8 degrees, and then SIMRAL is minus 10.8 degrees. So in this case, the wing root bending moment is computed to compare with that of the overdetermined trim solution. So the ZEUS overdetermined, our wing root bending moment was 3.5 times 10 to the 7, and then for the determined trim system, where we just arbitrarily imposed this condition where all of the control surfaces have to deflect by the same amount, we get 3.8 times 10 to the 7. So this overdetermined trim system results in a 7.9% reduction of the wing root bending moment in the 2G pull-up condition as compared to just the ZEUS simple determined system. So the 7.9% wing root bending moment reduction is actually quite significant if you are needing to design the structure based on the loads that the aircraft will experience. This 7.9% reduction in loads could be quite significant, and you can get quite a bit of weight savings in your structure design. ZEUS, we have that solution over here. This is unconservative due to the linear aerodynamic method.